Hello and welcome back to the YouTube channel of Canberra Engineering College. In this video session, we'll be looking into shift registers. So we will check out what are shift registers, what are the different kinds of shift registers, how do they perform, how basically you can load the data to shift registers and how the data can be shifted out of the shift registers, and which one is best among the shift registers that is available. So as the topic says, the shift registers is one of the basic application of a registers. So one of the application has already been studied, that is parallel adder with accumulator. The next application what we are going to study is shift registers. As the name says, shift registers are the devices which can shift the data that are present or that are loaded inside the registers. So whatever data has been loaded into the registers or whatever data is present in the registers can be shifted either to right or to left. So based on the ways in which you shift, you can call them as left shift registers or right shift registers. For example, let us take one of the shift registers or let us take one of the serial shift registers. Let us say this is the shift registers what I'm having. So as I have already explained to you, registers are made up of flip-flops. So let us say I have a 4-bit register here. I have 4-bit register here which is connected to a common clock. So let us say the data is loaded to the first flip-flop during the first clock edge. So my clock is connected here. So the clock is connected here and the data D0 is loaded to the first flip-flop. During the first clock edge, that is during the first positive clock edge that is occurring, the data or the first bit of the data will be loaded to the first flip-flop. That is, let me say, initially all my data were 0, 0, 0, okay? Let us say using the clear input, I have cleared all the data and during the first clock edge, I have loaded the first data to the first flip-flop. That is, 1 is loaded to the first flip-flop. That is, my first flip-flop data has become 1. During the second clock edge, let me say I am feeding next data to the register. That is what happened is at the outside I had a data 1, 1, 1, 1. So during the first clock edge, this LSB got shifted to the first flip-flop. That is why it became 1, 0, 0, 0. Got it? During the next clock edge, that is during the second clock edge, this 1 got loaded to the flip-flop and it became 1, 1, 0, 0. In the third clock edge, let me say during the third clock edge, this 1 will get loaded to the flip-flop and it will become 1, 1, 1, 0, right? During the fourth clock edge, that is during the fourth clock edge, it will become 1, 1, 1 and 1. You are getting this point? The data was present here. So this came here in the next clock edge. So it became 1 and 1. In the next clock edge, this came here. So it became 1, 1 and 1. And the last it came here. That is, it became 1, 1, 1 and 1. So let us say that as of now, the flip-flop is containing the data 1, 1, 1 and 1. So initially this 1 was present here. Later it got shifted here. Later it got shifted here. And later it got shifted here. As of now, all the 4 bits of data has been loaded to the register. This is what happens in case of your serial input, serial output register. So serially the data get loaded here. For example, if you say, if I go with the fifth clock, it will become 0, 1, 1, 1. That is, this data will go out. This will come here, this one will be coming here, and this one will be coming here, and it will become 0, 1, 0. So during 6th clock, it will become 0, 0, 1, 1. 7th, it will be 0, 0, 0, 1. 8th, it will become 0, 0, 0, 0. That is all the data what has been loaded will be going out of this particular register. That is what is your shift registers. The data what is present inside the register will be shifted to one of the flip-flops in the coming clock cycle. So let us say that I have a register which is having the data something like this. 1, 1, 1 and 1. So I'll apply the clock input. There are two chances in which my data will get shifted. One of the chances, as it is explained here, it will become 0, 1, 1 and 1, in which my data are getting completely shifted out of this register. If the register is a cyclic register, this data what is going out of the register will come back to the register and it will become 1, 1, 1 itself, which means that if you are shifting the data to the right, the rightmost bit which is going out of the register will come back to the register. So my registers can be cyclic register or non-cyclic registers also. Most of the times it will be non-cyclic only. So you can either shift the data from left to right or you can shift the data from right to left also. Both the ways it is possible. You can shift the data in both the directions. It is possible to shift it. Based on the ways in which you are going to load the data to the registers and remove the data out of the register, you have four different categories. First category, serial in, serial out. Serial in, serial out is what I have explained right now. See, first it was 0, 0, 0. I loaded the first bit of data. Later, second bit of data, third bit of data, fourth bit of data. By the end of the fourth clock cycle, my register had all 4 bits of data. That is, if it was 4 bit. In the fifth clock edge, one data was going out of the register. So if you need to load 4 bit of data into a 4 bit serial in, serial out register, it will take 4 clock cycles. So that is what is serial input, serial output. You normally call it as SISO. Serial input, serial out. So if you want to load 4 bit of data to the register and if you are planning to remove those 4 bit register or 4 bit data out of those register, you need 8 clock cycles, right? Fine. Next one is serial in, parallel out. Serial in, parallel out is like this. Suppose you have a 4 bit register. And I have the data 1, 1, 1, 1. So what you need to do is you need to give 4 clock edges if you want to load this data 1, 1, 1 and 1, isn't it? That was in order to load the data, it will take 4 clock inputs. And if you are planning to remove the data out of the clock, you need to give the 5th clock edge. During the 5th clock edge, my data will come out at a time. That is what it is explained. Input will happen serially, but output will happen parallelly. Input will be happening one by one, but output will happen at a time. That is what is parallel out or serial in, parallel out. Shifting can happen in any ways. You can either load the data from left or you can either load the data from right. That is based on the construction. That is what is serial in, parallel out. Next one is parallel in, serial out. Parallel in, serial out is you have a register like this. You will load the data at once from here. That is, in one clock edge, all the data will be loaded to the register. But removal of the data will happen serially. One by one, the data has to be moved out. That is what it is shown here. Parallel in, serial out. Similarly, parallel in, parallel out. Parallel in, parallel out means you have a register, something 4-bit register that it is shown here. So 1111 is to be loaded. So those loading will happen in one clock cycle and removal of data will also happen in one clock cycle. So these are the 4 basic categories of registers. That is, shifting will happen only in case of your serial in, serial out and serial in, parallel out and serial serial in, parallel out and parallel in, serial out. So shifting will happen only in this. That is, data will be getting loaded from one flip-flop to other flip-flop. It will start moving from one flip-flop to other flip-flop. That is what is called as shifting. So it will happen here in case of serial in, parallel out and in case of parallel in, serial out. That is what is your shift registers. Moving on further. This particular block diagram explains you a 4-bit shift register with serial input and output constructed from D flip-flop. So this is what I had explained to you in the previous slide also. So the circuit, what you can see here, this is your 4-bit shift register. How the data are loaded? Serially. How the data are removed out? Serially. So this is your serial in, serial out register. So this is constructed using your D flip-flop. So you can see data inputs, outputs, clock input, chip enable, all the inputs, whatever I could see in the D flip-flops are all present even in this. So if you want, you can add one more additional input, which is clock. So which is clear. So what you do is, initially you will give the clear input. After the clear input is given, you will keep the data ready at the input side. Where will you keep the data ready? The data will be kept ready at the serial input. For example, your data is 1010. Let me say my data is 1010. So you need to keep this data 1010 at the serial input. Later, you need to give the clock input. During the first clock input, your first 0 will enter into the flip-flop, and this will be 0 because you have used a clear input, right? So initially it was 0, 0, 0, 0. Because of the first clock edge, my first 0 entered into the flip-flop. During the second clock, this 0 will come here, and this 1 will get loaded to this particular flip-flop. So it will become 1, 0, and the zeros will remain as such. During the third clock, what will happen? During the third clock, this 0 will come here, 1 will come here, and this 0 will be loaded here. So it will become 0, 1, 0, 0. During the fourth clock, what is going to happen? During the fourth clock, this 0 is going to come here, this one is going to come here, and this 0 is going to come here, and this 1, what is left out, will be coming here, making it 1, 0, 1, 0, which means that in order to load 4 bit of data to a 4-bit serial input, serial output register, you need 4 clock edges. Now, if you want to remove the data out of this register, you need to give the clock 5. So this 0 will go out, this 1 will come here, this 0 will come here, this 1 will come here, and this will become 0. If there is no data to be loaded, it will become 0. So you need 5, 6, 7, 8 clock cycles in order to load the data to this register and remove the data out. So how does the shifting happen, sir? After I load the data, when I give the clock edge, will it happen? No. If you want the data to be shifted, you need to keep your shift, or you need to activate your shift signal. For example, if you have the data 1010 here, and if you give the clock input and if you give the shift high, this 1 will come here, this 0 will go here, this 1 will come here, and this will get loaded with 0. This is what has been explained here. See, this is your serial input, the data Q3. Your shift is already made high. This is your Q3, and you can see this data moving here. In the next stage, this data is moving here. The same data is moving here. Q4, this is moving here, which explains you the timing diagram of your serial input, serial output register. So you can say this is 1, 0, 1. Later it will become 0, 1, 0, 1. This will become 1, 0, 1, 0. Again, this will become 0, 1, 0, 1. This will become 1, 0, 1, 0, 1. So you can see here, 1 which was present here has been shifted here. You consider this. You consider this dotted. So 1 which is present here, in the next clock cycle it is shifted here. During this 1 has been shifted here. That 1 has been shifted here. That 1 has been shifted here. So this will be your flip-flop. This will be your flip-flop 1, second flip-flop, third flip-flop, and this is your fourth flip-flop. And this are with respect to your clock edges. So you can see the data getting shifted with respect to your shift input and with respect to your clock input. Moving on, next we have 8-bit serial in, serial out shift register. So what we saw previously was, this was a 4-bit shift register with serial input and serial output. We have the advanced version of that, what we can see further. So the changes what you can see there is, here you are using only 4 flip-flops. In the 8-bit, obviously when I speak about an 8-bit register, it should be having 8 flip-flops. So this is what you can see here. So serial input is this one. So the data will be, you can construct register using any of the flip-flops as it is explained here. This basically becomes a D flip-flop itself. In fact, it has been shown as SR flip-flop, SR flip-flop. You can see that input has been inverted. So obviously this has become a D flip-flop. So there are 8 flip-flops which are connected in series to a common clock input, which means the clock is connected synchronously to all the flip-flops. And I can say that I will place the data something like this. I'll place the data. Let us say that I'll be placing the data 0, 0, 0, 0, 0, 0, 0, 1. So during the first clock edge, let's go with this. During the first clock edge, let us say that it is all cleared. Okay, let's say that it is all clear. The initial data which are present in the flip-flops which is forming a register or which has been turned out to be a serial register is all cleared, and it was initially having the data 0, 0, 0, 0, 0 and 0. So during the first clock edge, 1 will get loaded to this register, and this will all be zeros as it was previously, right? During the second clock edge, this will become 0, 1. During the third clock edge, it will become 0, 0, 1. Fourth clock edge, it will become 0, 0, 0, 1. During the last clock edge, it will become 0, 0, 0, 0, 0, 0, 0 and 1. If you give one more clock edge, if you go with one more clock edge, this will once again come back to 0, 0, 0 itself, because this one will be going out of this particular register. The same has been shown in the timing diagram also. So you can see the clock edges here. You can see the serial inputs here. So this is S0. S0 is, that is the output here. After the occurrence of the 8th clock input, you can see this particular input, what was being fed here, has been shifted by 8 position, or it has come to the 8 register. So the input, what you can see here, this input you can see here, which has been shifted by the same positions in the shift register. So this is what is your 8-bit serial in, serial out register. Normally, when I speak about the registers, I have already explained. One is serial input, serial output. Other one is serial input, parallel output. Other one is parallel input, serial output. And the last one is parallel input, parallel output. Out of all these registers, parallel input, parallel output is the fastest one. You can load the data into this parallel input, parallel output register in one clock cycle, and you can remove the data out of this PIPO register in one clock cycle, which means that whatever number may be the bits, it may be an 8-bit or it may be a 16-bit or it may be a 32-bit, the loading of the data will happen in one clock cycle, and the removal or unloading of the data from this register will happen in one clock cycle. So totally it will be taking around 2 clock cycles to finish up the task. So comparatively, PIPO is one of the fastest one. After this PIPO, serial input, serial output and parallel input, serial output will be holding the second place with respect to speed. And SISO or serial input, serial output will be one of the slowest one, which will be holding the last position with respect to the speed, with respect to loading of and unloading of the data. Moving on next. This is your 4-bit parallel in, parallel out shift register. So this is your PIPO, which I said to be the fastest one, right? Which I said to be the fastest one. So let us check out a little bit detail about this. So you can see here, this basically, the thing what I can see here is basically a universal register. Why do I call it as a universal register? Is this register can perform the task of all the 4 registers. That is serial input, serial output, parallel input, serial output, and parallel input, parallel output. So you can see here, the data can be loaded parallelly, or you can load the data serially. You can remove the data parallelly, or you can remove the data serially also. So this basically is a universal register, but for our study purpose, we will consider it to be a parallel input, parallel output register. So what you can do is, how do you do that is, initially you will load the data. Initially you will load the data by giving the clock edge. As soon as you load the data by giving the clock edge, the data what was present here will be inside the register. That is D3, D2, D1, D0, or D2, D1, or D3, D2, D1 and D0 will be loaded into the register. After the data has been loaded into the register, if you give one more clock input, the data will come out of the register through Q3. So then the data here will become D3, D1, D1 and D0, which means the data was getting loaded in a single clock edge and the data was moving out of the register also in the same clock edge. Whereas if you want to make it as a serial input, serial output register, you can activate this SI signal. You can make SI equal to 1. Or you can make this SI equal to 1. Once you make this SI equal to 1, the data will get loaded serially. Similarly, you can make S0 equal to 1. When you make SI equal to 1 and S0 equal to 0 or S0 equal to 1, data will get in serially and data will go out serially. So this basically is a universal register which has been taken to explain a PI/PO register. In fact, the advanced part of this or an advanced version of this has been shown here. So what they are doing here is, as I said you, this is an universal register which can be used to perform all the 4 tasks. So here you can see they have connected muxes. They have connected mux at the input of every flip-flop. So by connecting the mux at the input of every flip-flop, they can, for example, when it is made 0, 0, it performs as a SISO. When it is made as 0, 1, it performs as a SIPO. When it is 1, 0, it performs as a PISO. When it is 1 and 1, it performs as a parallel input, parallel output register. So you can implement the same register, or you can implement a register using a flip-flop, and also you can implement it using the muxes. So loading of the data, what you need to do is, initially if SH equal to 0 and if L equal to 0, even though you give a clock input, the data output Q3, Q2, Q1 and Q0 will change because no new data has been loaded inside, neither no new data will be going out of the register. When shift is equal to 0 and L is made 1, new data will get loaded to the first register, or new data will get loaded to the second, all the registers. Suppose if it is 1 and 1. Suppose if the mux is giving an output of 1 and 1, it is going to select an operation PIPO. Then all the 4 registers will get loaded with the data, isn't it? When shift is equal to 1 and L is equal to 0 or 1, the data will start shifting. So it is up to you people what function you are going to choose. All the things are given here. Whether you want to load the data serially, whether you want to load the data parallelly, whether you want to shift the data, all the options are given in the registers, which means that normally my registers are available as universal registers. Universal registers means it is up to you people what you want to use this register as, whether you want to use it as serial input, serial output or parallel output. And in order to make it as serial input, parallel output or any of the options, there are inputs given. So based on the values those are given to the activation signals, the entire circuit will act as any one of the 4. So this is regarding your serial input, serial output, parallel input, parallel output, parallel input, serial output and parallel input, parallel output register. So normally they will be asking you regarding serial input, serial output, or most of the times they will go with parallel input, parallel output. The chances of questions on PISO and SIPO are comparatively less, even though in the syllabus or in the curriculum for you people, they have not prescribed any of the registers in detail. They have just specified shift registers. So you people need to be concentrating probably on this one, that is on the serial input, serial output, or maybe you need to concentrate on the universal registers with the muxes. And as I explained to you, the muxes are used to make a choice between the 4 types in which the data has to be shifted. And most of the registers, as I said you, are non-cyclic. That is, the data going out of the last register will be completely lost. It cannot come back to the first register. Moving on further. Some of the applications of your shift registers. So you can use your shift registers to make many of the applications. one of the applications what it is called as ring counter. Ring counter. The second application here is twisted tail counter. In fact, this is not very briefly given to you in the syllabus, but still let us know about this. The third one is called as linear feedback shift register, LFSR. So ring counter, what basically is this particular ring counter? If you can check the circuit here, this is a register, normal register. So what kind of register is this? This is your serial input, serial output register. And this is a cyclic one. Cyclic one in the sense, the output of the last register is not going out, it is going to come back to the very first register. So what you can do is, if the non-inverted output, see I'm drawing here, if the non-inverted output of the last register is taken and if it is connected as input to the first register, so let us say the numbers were 1, 1 and 1. So during the first clock edge, it will be 1, 1, 1. Second, also it will be 1, 1, 1. During the third, it will be 1, 1, 1. During the fourth one, also it will be 1, 1, 1. Which means that the same sequence is going to repeat. The same sequence will be repeated in this particular register. Or if it is, for example, if you say it is 1, 0, 1. If it is 1, 0, 1, the next instant it will become 1, 1, 0. The next instant it will become 0, 1, 1. The next instant it will become 1, 0, 1, isn't it? Which means that these three sequences are going to repeat. After 101, it will again become 110. After that, it will become 011. So again, those three sequences are repeated. A register which has been designed in such a way that in which the non-inverted output of the last register has been fed back as an input or data input to the first flip-flop is called as ring counter. So ring counter normally keeps on repeating the sequences as it is explained here. For example, if it was 100, 101, so 1 will come out, it will become 110. Again in the next case it will 011. After that it will once again come back to the same sequence. So a register or a shift register which has been designed to repeat the sequences, it is called as ring counter. That is what is ring counter. Other one is twisted tail counter. Twisted tail counter is a counter in which the inverted output of the last flip-flop is taken and it is connected back as input to the first flip-flop of the register. In this case, what will happen? Let's check out. See here. Let us say it is 101 is the first thing. Later, what will happen? This one will go get inverted, right? So it will become 0, 1, 0. Later, it will become 1. This will be inverted. 0, 0, 1. Later, it will become 0, 0, 1. And this will be repeated. For example, let's say the initial input is 0. So this will be inverted. It will become 100. Later it will become 110. Later it will become 111. Later it will become 011. Later it will become 010. So in case of your ring counter, normally these three sequences will be repeated. Isn't it? Whereas if you design it in such a way that where the inverted input is connected back as input to the first flip-flop, in addition to these three, additional 3 inputs will be added on. So this setup is called as twisted tail counter. First one is ring counter. Ring counter is same sequence repeating again and again. Whereas in case of your twisted tail counter, additional 3 sequences will be added up and those sequences will be repeated in case of your twisted tail counter. Moving on further, the last application of your shift register is linear feedback shift register. So this one, let's consider this to be a register, okay, 3-bit register. The register was having the data 0, 0, 1. It was having the data 0, 0, 1. The first bit and the last of the register is connected to an XOR gate, and the output of the XOR gate is connected as an input to the register. This is a shift register itself. This setup is called as linear feedback shift register. So check out here. Initially my data was 0, 0, 1, 0, 0, 1. During the first clock age, because of that, it became 100. Later it became 110, 111, 011, 101, 10010. Again, this will be 001 itself. So, which means that this will display 6 sequences very similar to the twisted tail counter. But in case of twisted tail counter, we connect the inverted output. But in case of your linear feedback shift register, we connect the output of the last register and the output and the data of the first register to an XOR gate, or you can connect it to the XNOR gate also. This setup is called as linear feedback shift register. So this may be your register, 4-bit register. Here you connect a XNOR gate, and this one is also connected here. The output of this is connected back here. So this forms a linear feedback shift register, where you are going to generate multiple sequences. That's it. If it is a ring counter, it is going to generate the sequence that is equal to the number of bits. See here. If it is a ring counter, it is going to generate the sequences. For example, if there are 3 bits, it is going to generate 3 sequences. Whereas if it is twisted tail counter or linear feedback shift register, it is going to generate the sequences which is 2 times the number of bits that is stored. See here, you can see 6 sequences. Even here, you can see 6 sequences which has been generated. So this is regarding the shift register and applications of linear feedback shift register. Thank you.